All right, so I'm going to move pretty quickly because some of the overflow slides from my Monday presentation are in here as well. So just a note on MeerKAT. MeerKAT's supposed to be this all-singing, all-dancing instrument that tries to be everything for everyone. And here's just a list of some of the things we need to do. And at the time of design, some of it actually wasn't even defined. So it was very hard for us to try and spec the system. And the basic signal path looks something like this. On the left, you've got the antennas coming in. It goes through a band selection process and then straight into this giant switch. And then we do correlation and beamforming and so on. And then there's that sort of hard real-time. And then there's a sort of soft real-time system that does further processing on it and archiving and exposes all this stuff over the interwebs, all very nice. But this has allowed us to sort of split the system into three parts. And these are three different teams within the organization. There's the digitizer team, and that's essentially sort of RF conditioning and the analog to digital conversion. And then there's my team, the correlator beamformer team, the DSP team, and then there's the SDP science data processing team. And this maps quite nicely actually into the network architecture. So down on each antenna, down in the pedestal, there's a network switch. That's the first switch in the system. And its purpose is essentially to aggregate all the different feeds that sit on the turret that Francois described and drive the backhaul link to the central processing facility. It then comes into what's currently a 40 gigabit per second switch, which does all the hard real-time stuff. And then it goes into a slower network with PCs with GPUs in it for further processing. Okay, so first slide, the good bits about our network and the things that work well. It is a full crossbar, any-to-any switch. There's no oversubscription. This means you can do arbitrary data routing. You're not limited by the switch architecture or board interconnect. You can route data anywhere you want. It's based on something called a closed topology, which we'll go into in a few minutes. It's very scalable, and this gives you maximum flexibility, which we sort of needed because we didn't know what we wanted at the start. Our initial deployment was actually a 10 gig network, and we upgraded to 40 gig when we switched from Roach 2 to Scarab partway through MeerKAT deployment. And we've started thinking a little bit about 100 gig Ethernet as our next step. We actually use a custom round-robin based load balancing algorithm, which I'll also chat about in a little bit. It turns out this is perfect for all current radio astronomy use cases and is better than the IETF mandated hash algorithm. All the data in the system is multicast. We only unicast for control, basically DHCP and ARP, the standard network. No radio astronomy data is unicast anywhere. And also just a note, people often argue and complain that, oh, this is all good and well, but it's too expensive. And just a point, you can in general build an interconnect like this for about 10% the cost of the signal processing system. So as an overall fraction of the cost of the system, it's not that huge. Here's just a picture of some of the install process. These are the switches where the antenna links come in. So these are 40 gig long range transceivers, and the fibers come in here from the antennas. There are 16 per these switches. There are 4 of them. And then these are the active optical cables, which I spoke about on Monday, that interconnect these switches to the rest of the network fabric. Here's just another picture of the install. It gives you some sense of the scale and all the cables coming into each rack. These are some of the fiber trays on top. There's well over 1,000 of these things. Why do we need all this flexibility? Here is a slide deck from 2010 that I resurrected and found here that we'd predicted we would need 196 40 gig ports. By 2011, the number had gone up to 266. By 2015, it had gone up to 291. Would anyone like to guess how many ports we have now? 648. And only 56 of them are spare. Where are all these ports going? Well, the bulk goes to something called user-supplied equipment. These are external people who've brought their own computers, their own processing systems, and they want to plug into our telescope and get copies of the data and process it themselves. There's quite a lot of this, much more than we ever expected. Someone's bought a pulsar timing backend. There's a 500 beam GPU-based beamformer, a pulsar search backend, a transient search backend using beams and an imaging plane one. SETI's here in a big way. There's even an S-band receiver. So there's a lot going on. Our own processing system, this is a sort of snapshot of some of the pipelines and the colors of from a few years ago, how far we were with the then development. I'm not going to go into any of this detail. Suffice to say, there are a lot of different pipelines that can be instantiated, and it's all done dynamically. Inside this giant switch, you get a lot of data flowing every which way. You can duplicate the time domain data with this multicast and run multiple correlators concurrently on the same data, maybe some being wideband, some being narrowband, like Andrew van der Bell just spoke about. You can have pulsar processors and beamformers and all sorts of things running at the same time if you want it. Here's a picture of some of the scarab racks to give you a sense of what this actually looks like. There's just a whole. We put 32 of these in a rack, and these are network switches in between, which we mount back to front, so that all the cabling in the rack is actually located at the back. So the front looks all nice and neat for these pretty pictures. Okay, I want to talk a little bit about scaling Ethernet. Most local networks, like our internet connections here, would be based on some sort of a tree structure, which might look something like this. You've got all your computers at the edges, and they connect into some switches, and those switches connect to more switches, and it sort of funnels up, and eventually you get down into the spine or the trunk, and it's routed up into the internet. There are a few problems with this approach for our purposes. For one, it offers no resiliency. If this link were to break, all of these computers would lose their connectivity. It also doesn't offer any full crossbar communication. If one of these computers wanted to talk to one of those computers, it would have to go back via this link. And if all of these guys wanted to talk to all of those guys, typically these links don't have enough bandwidth to do that. So we need a better topology. And there are lots and lots of ways to do this sort of thing, depending on what your goals are and what you're trying to trade off. So let's talk a little bit about what we want to do. We want to be able to add nodes and scale up as we want. So this whole thing needs to be scalable. We don't want to take down the whole network if a client or switching node fails. So we want some sort of resiliency and robustness. If anyone remembers ThinNet with the BNC connectors, some new computer wants to join the network and the whole network goes down. That's no good. We want this full crossbar non-blocking switch. We want any node to be able to communicate with any other node, and this would allow nodes' functionality to be interchanged. 1 minute a scarab board can be an F engine, the next minute it can be an X engine. If the board fails, we can reroute its data somewhere else. We want it to be multicast capable. This was a key thing for MeerKAT from the get-go. We want commensal observation, and of course we want to do this all very cheaply. So enter the closed network. Charles Close figured this out back in the 50s. So that Bell Labs could build large telephone networks out of small switching modules. And you can look this up on Wikipedia for the details, but in short, it's defined by 3 variables, N, M, and R. You build it out of little M by N size switches, and you put lots and lots of these things together. So if you have R of these things on the ingress phase, it goes through a middle layer to an egress phase. Bear in mind that this was designed in the era of circuit switch networks, not packet switch networks. So it's done with the concept of connecting an ingress node to an egress node, a caller to a destination, and that circuit is then switched into place. But the logic is the same for packet switch networks. There are always an odd number of layers in this sort of topology. So there are 2 important results that come out of this. For a strict sense non-blocking switch, that is, if you want to be guaranteed that you can always get to your destination regardless of what state the network's currently in, then for N input ports, you need 2 N output ports. So you need twice as many uplinks as you have links to clients. But if you're willing to rearrange things in the network a little bit, you can actually get by with N equals to M. So the same number of uplink ports as client ports, which intuitively makes sense. Then you've got the same amount of bandwidth coming in and going out. So I'm going to go into a little bit about the implications of this now. But you're going to see the diagrams are going to change shape a little bit. And the reason for that is, in an Ethernet network, all ports are bidirectional. You can send and receive, as opposed to an ingress and an egress. So if you fold this whole diagram over about the central point and we rotate it 90 degrees, then you get a diagram that looks like this. So here are all your computers. These are send and receive ports. This is what we call a leaf layer, and this is the spine layer. And it's just a bit of common terminology. Okay, so here's a scenario in your clos network. Imagine you have A, B, C, D, and E over there. A is connected to A down here via that middle layer. B is connected to B down here via that middle layer. C is coming from down here and connected up to C there. And D is connected over here. Now, user E comes along, and he wants to talk to E over here. But there's a problem. So E there has two output choices. And if he takes the first one, he'd go through this switch. And this switch would have to connect here to get him to E there. But you can't, because this link's already used. And if E were to try and use the bottom link, it would need to come out here and go through here, which is also already used. So you have a problem. And in this case, you have to rearrange things, because M equals N, you have 4 inputs and 4 outputs. So you can do this. If we rearrange D and reroute D through the top one there, then it frees up this one for E. Does that make sense? Okay. So how do we do this in Ethernet? It turns out you can't, because Ethernet nodes don't communicate with each other, and in order to do that, you need something that has an overview of the entire system that can figure out who needs to be routed where. This is hard in Ethernet, where each node operates independently and doesn't have a view of the rest of the network. And there are kind of two obvious ways you can think to do this. We can try and organize the routes to prevent overloading, and as I've just said, that's really hard. Or two, we can try and load balance each data stream to use all the links all the time, a tiny fraction of all of the links. You might wonder, well, why can't we just buy one big switch, which doesn't have this problem of trying to route things through these little dinky intermediate switches? And it turns out inside these boxes is exactly the architecture we've just described. There is no such thing as a single giant ASIC with hundreds and hundreds and hundreds and thousands and millions of ports. And I want to point out that not all of these boxes are made equal. Here is an example of Arista 7500 and an Arista 7300. They both have hundreds of ports. They're both based on a close-in-the-box architecture, but they are not created equal. The 7500 does what I described at option 2. It shares data packets over middle layers. So any packet that comes in, it distributes across all of the switches in that middle layer. The 7300 distributes streams over the middle layer. That is, for a given source and destination, the 7300 will always pick a single path through the system, whereas the 7500 will spread that out over all available paths. There's also a big difference in buffering capability. The 7500's got gigabytes as opposed to megabytes. And you pay quite a big premium. It's almost double the price for this. But you get perfect load balancing and hence lossless operation under any conditions on a 7500. And then I also just wanted to point out that there's some practical implications for going for one of these big switches. Anyone who's ever tried to route 500 cables into a few U will know what a problem this is, and it's really difficult to maintain that. Also, while these switches might be very reliable, it is a single point of failure, and you can't really piecemeal, you can't upgrade these things. The manufacturers will promise that you can swap out line cards and that they're forwards and backwards compatible, but you actually very rarely get full functionality with future line cards unless you replace all the innards of these switches, which costs a lot of money. So don't fall into that trap. How do they deal with this in industry? Equal cost multipath, that technology I spoke about on Monday. Given a set of equal cost paths, a hashing algorithm is usually used to select the link to use. Inputs into the hash, which are often configurable, are typically things like the source or destination IP, MAC address, or port. And then it will pick a single link for that. And you'll recall from Monday that you have to do this. You can't spread out packets necessarily because you can't guarantee that the links always behave the same way. This sort of randomizes the link selection. So if you give it enough entropy, if you have lots of different IPs and MAC addresses and everyone's talking to everyone, you kind of get pretty good load balancing. but it is non-perfect. So if you're trying to operate your links at 95% of their rated capacity, as we do in MeerKAT, then you have a problem if you have a 20% imbalance. So you could just over-provision by 20%, but it's a little bit wasteful. Then the ugly buffering issues. Imagine you have 4 senders there trying to all send to one guy here. At some point, these things funnel in, and you get potentially buffer overflows there if that switch can't buffer all those packets. You could change things and reroute them all through a spine, the same spine to get there, but you have the same problem. You've just moved the buffering problem from that node to this node. How do you deal with this? Well, you just throw memory at the problem. On an FPGA, it's actually pretty easy. You can coordinate your transmitters so that you interleave or sequence their output so that only one sender is ever sending to a receiver at a time. But you can't really do that on a computer because you don't have precise control over the packet transmission time. So you just have to throw memory at it. MeerKAT's old Switch X-based system has about 100 KB per port. If you're sending jumbo packets, that's not a lot of packets, 10 packets and you're done. Modern Switch ASICs have 16 sort of megs of shared buffers, so you can do a lot better there. What about multicast? Well, I'm going to have to rush through this, so we don't really have much time. We actually do this all at layer 3. It gets around a problem where you can, in layer 2, land up with these sort of broadcast storms, where even if you only have one sender and one receiver, the data ends up being blasted all over between these switches because they can't control multicast between them quite properly. You don't have this problem at layer 3. You get the expected behavior. One person sends something, it goes to a single defined point, and from there it gets distributed out to any receivers who are interested in that group. The protocol is called Protocol Independent Multicast, PIM. It comes in a few different flavors. We use PIM bidirectional. And we've changed the IETF-defined hashing algorithm for a round-robin version, which gives us perfect load balancing in the case of radio astronomy streams. And if you add another transmitter who's transmitting to the same group, he will also always send that multicast traffic to a defined point. So this is all hidden from the end nodes. The network will know to do this. So if you send data to a given multicast group, it's always routed in the same place in a PIM bidirectional network. A little bit about the future of MeerKAT. What are we thinking moving ahead? We think we are going to start using some of these off-the-shelf cards. So the U280 at this point looks really interesting to us. It's got 8 times the compute capacity of a Scarab and costs half the price. So that looks quite nice, and so we're investigating this at the moment. There we go.
You mentioned that you changed the hashing algorithm to a round-robin algorithm. That means that you get into these commercial switches and mess with their guts?
Yeah, so actually, we went through quite a long process of evaluating different switches. I was in very close contact with 7 vendors, 7 of the big players. It lasted about 2 years. We threw around all sorts of ideas for topologies and protocols and tried lots of different things. No one passed first time. They all failed our tests, so everyone promised they could do it. And after a lot of back and forth toing and froing, we eventually sort of stumbled upon this solution. And there were 3 of the vendors who implemented it or were willing to implement it for us. So it's a slight deviation from the IETF mandated hashing algorithm. And it's an optional thing. You just give a command line on the switch and say, hey, switch to round robin. Yeah. Yeah.
How would we get a hold of that? Like, is it possible for me to ask you what those manufacturers were, or how do you get that extra?
Yeah, I'm under NDA a little bit, but let's have a chat if you're interested in that. I mean, I can tell you we're using Mellanox switches at the moment, and Mellanox have changed their IP stack from the one we're using to a new one, and actually a lot of this functionality has not yet been implemented in the new version, though it will eventually come. So you actually have to roll back to an old version to get all of this stuff at the moment. And Cisco and Arista have also indicated a willingness to do it, but I haven't actually played with their products in the last little while, so I'm not sure if it's there, if it's available. Yeah.
Jason again.